Thank you very much. I'm also very glad to be here at this conference and that I may present to you this new technology, power to gas. It's a buzzword all over Germany, in fact. In fact, I'm coming from the country that Wolfgang Streicher just mentioned. It's the country where cars may go 250 kilometers per hour. And I'm also working for a firm who is building these cars. So you might think, what is this guy doing here, telling us something about renewable energy? But in fact, Audi is, and this is why I'm working for Audi now, Audi is currently going a path which is extremely new for any automotive producer. Audi has decided to produce fuels that are 100% renewable, and I'm going to show you one of these projects they are doing. I'm going to follow the following agenda. So first I'd like to go into the German system of the German energy system, and Professor Bukis showed us a global picture and global scenarios. So I'm focusing on the German energy system, and I will also take the axiom that the German politicians are currently following. They want to go 100% renewable. If it's 100% or 80%, it's to be debated, but they are following a path which is very radical as compared to the rest of the world. And they want to do this also with economic growth, of course. But there are a lot of problems, and Professor Bukis has already mentioned some of them. If you build a lot of renewable energy which is fluctuating, you have a problem that you need backup plants like gas-fired power plants, and you also need to build up the electricity grid. And some of these problems have not been mentioned in the discussions in Germany up to now, but currently there's a huge discussion as to what problems will still occur and how to deal with them. So I'm starting with this question, are there any problems involved going 100% renewable? Wolfgang Streicher showed us that in Austria we have a good situation to start with because we have a lot of hydro, but in Germany they don't have hydro. So let me show you some numbers from Germany. You can see here three columns. The first one is from 91, the second one from 2009, and the third one from 2020. What you can see here is the total annual energy consumption in all energy sectors, which means it's not only electricity, but all energy sectors. And you can also see this green share here is the renewable share, including hydro. And this renewable share in 91 was negligible, so you can see it's very small. It's maybe below 1% even. But you can also see that Germany made great efforts. They introduced the EEG in 2000 and so on. And Germany succeeded to increase this 1% to 11% if you compare it to the whole energy demand. So it's not only electricity, as I said. And they are planning to go up to 14% in 2020. That might be exceeded because these numbers are before Fukushima. As they're getting out of nuclear, they might be even more. So what you also can see is the fossil imported energy is staying about the same. This has something to do with the fact that the fossil national energy will be decreased because the lignite is not a coal type that is favored in Germany because it emits a lot of CO2 equivalent, as you also know. What you also can see is that Germany is doing a great job in becoming more energy efficient, because you know that Germany has a growing economy, still in the crisis, a growing economy, but still they are succeeding and planning to continue to decrease the overall energy demand. If we're looking at the sectors, you can see that electricity is part of the game, but not all of the game. It's about 20%. Mobility is another 20%, and heat is 40%. Industry is also about 20%. So what we can see is if we want to go 100% renewable, it's of course not sufficient to make the electricity sector renewable. We need to make the heat sector and the mobility sector renewable. As Wolfgang Streicher showed for Austria, we have to show this somehow for Germany also. And what is going to happen if we do this? Let me take you to a journey to 2050. There are some scientists in Germany who made a study for 2050 where they imagined that now looking only at the energy sector, electricity sector, where they imagined that 100% of the electricity that is needed in Germany is produced by renewable energy. And this is what came out. What you can see is that on average it could be done, but per hour it could not be done. And why not? Because it's fluctuating enormously. What you can see is this Arrhenius pattern. It's the residual load in gigawatt. So the residual load is the load, so which means the total energy demand in 1 hour minus the energy produced in this very hour. So if you have here some red patterns, it means you have an energy deficit and you would need to produce the energy from somewhere else. If you want to meet the demand, because you have to meet the demand, if not, you have a blackout. And if you have a blue situation, then you have too much energy in the electricity grid, and you would need to either throw the energy away, or export it, or store it. And what you can see, interestingly, the red patterns and the blue patterns are about the same. So if you make an integral over the blue and an integral over the red one, it will be about the same size. So it would be a great thing to take the blue, store it, and use it when it's red. This would be the solution. And this is a storage problem. You need to store the energy when you have it, and you need to take it out when you need it. And then let's look at storage technology. The main storage technology we know is a pumped hydro storage. And this is a great thing because it has a high efficiency and it's a known technology and it works, and Austria is very good at it, so it would be good too. But in Germany, there's not enough potential for that. By far not enough potential. And pumped hydro has another problem. If you pump up the water, after 2 days, about 2 days, your upper basin will be full. But the problem is that the wind, this is mainly wind which causes these patterns here, can blow for 2 or 3 weeks. And so you can see these blue patterns can be weeks. This is a month, so this is about 3 weeks. You would need a basin that is so big that you can store 3 weeks of energy in it, which is impossible to build. In Germany, it's completely impossible. So you would need, in fact, you would need a storage technology that is able to store energy for a longer time than 2 days, let's say. And this is a far future scenario. It's just 2050. You can say, well, this is not interesting. It's just a future thing of some scientist. That might be true, but let's look at 2020. We made another simulation for 2020 with another institute. And you can see here the power in gigawatt. This is the demand. The red line is the demand again. The blue lines is the offshore wind energy, if it's dark blue, and the onshore will be light blue. We are now in the year 2020, in your imagination, and we have installed capacity following the National Renewable Energy Action Plan of Germany for 2020, which might be even exceeded because of Fukushima. There's also pre-Fukushima data, so it might be even more. But let's assume it's this. And now imagine we are in the month of May. This is the month of May, and we are. You remember that on weekends the electricity demand is lower. So you can see here Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. Okay, so it's very neatly describing the situation. And what you can see is that on some Sundays, let's say, you have 100% renewable energy coverage. So you produce all the demand by renewables. But on the other hand, when there's no wind and when it's night, on this Tuesday, you have 0 renewable energy in the grid. So this is one of the main problems we encounter in renewable energy ramp up, that we have an extreme fluctuation in production, and the fluctuation in demand is the same as all the time. It doesn't change. It's the same pattern. It's the human pattern of sleeping and working. But the production does not follow this pattern anymore. And so we would need a technology that goes up here and provides energy and then goes down when there's enough energy and so on. And as you can imagine, that to follow this path here, to follow this ramp up and down, it's a challenge for any power plant, even for a gas-fired power plant. It will cost a lot of efficiency running up and down a power plant like this. And this is going to happen in the near future. It's 2020, and it's not a very ambitious scenario. It's a normal scenario. It's a National Renewable Action Plan before Fukushima. We will see these problems, and in Germany they are discussing these problems very much at the moment. The Germans call this Energiewende, so change of energy system or something. This is the buzzword. So let me summarize. Of course, my introduction ends here, and let me summarize what is happening here. We will have a lot of problems if we're going to 100% renewable, and we will have problems that we didn't consider yet. We will have problems in the distribution grid. There will be capacity problems in the distribution grid. In the transmission grid, there will be large investments in this grid. There will be fluctuations of residual load. There will be demand for storage capacity smaller than 2 days. This could be covered maybe by pumped storage. But there will be a demand for storage also larger than 2 days. And in the end, we are ending up with an increase of these problems. This is just a schematic line. It should just indicate that the importance of the problems will rise. The larger the share of the renewable energy in the grid will be. And this is only 20% of the problem. As you remember, we have only discussed about the electricity grid at the moment. But then we want to decarbonize the heat and industry sector, as Wolfgang Streicher illustrated for Austria before. And then we want to decarbonize the mobility sector in the short range. And even if the people would be willing more and more to take the train and go by bike and everything, there will be a quite substantial share of people and trucks and so on, which have to go long-range mobility. And these are growing problems that we have if we want to go 100% renewable. So let me tell you, and let me agree with you, I think we can go maybe 100% renewable, but we will encounter a lot of problems. How could we solve these problems? Should we just scrap the 100% renewable vision, or is there a solution? Of course, I wouldn't introduce it like that. There is a solution, as we think. And one of the solutions, and one of the important solutions, is this power-to-gas technology. So what is this power-to-gas technology? Let me just take a bit of water. The power-to-gas technology needs electricity, water, and carbon dioxide as input materials or input components, and it will yield oxygen, hydrogen, and methane as output. Let me go with you through this graph here. So the schematic flow chart of the power-to-gas process is as follows. We take electricity, we have an electrolyzer, which makes hydrogen, and we have the oxygen is not depicted here. It will be emitted to the atmosphere. The CO2 needs to be taken from some source. We need pure CO2 to run this process. We have here a tank that stores the intermittent CO2, And then we take the hydrogen, the CO2, we go into a methanization reactor and we produce methane. And what you also can see, you can also, of course, take the hydrogen directly and feed it into the gas grid. And here is the thing. We feed it into some grid. And now let's look at the situation, how the gas and electricity sector is run in Germany. It's just a very simple picture. We have an electricity grid, we have wind, solar, and all other kinds of fossil energies. It's just all kinds of energies. And on the gas side, we have a gas grid, which is very dense in Germany. We have a large gas grid, and it goes everywhere in all households, or in many households. And we have also gas storage facilities, which are depleted gas caverns where the new gas can be stored. So we have a grid and we have storage. And what we are doing at the moment in Germany is we take the gas and we convert it to electricity. So this way. Okay. What happens if we take this and put it together? Then we have a coupling of the gas grid and the electricity grid. And so the technology takes energy when it is available, electric energy. It produces gas, and it stores it in the gas grid. And the gas grid has one large advantage. It can store gas for a long time because it's 200 terawatt hours of storage capacity in the German gas grid. This is 1/3 of the German electricity consumption per year. So you can store, let's say, for 4 months, you can store the gas in the gas grid, which means it's a long-term storage technology. And now it opens a new path. We had this path before, it's a one-way, and it opens a new path, electricity to gas. And this means that we can cope with this, because we can store and we can produce using the gas-fired power plants. And we can do another thing which has not been mentioned before. We can use the gas in all sectors. This technology makes two things. It solves a storage problem, and it solves the decarbonization problem in the heat industry and mobility sector. Of course, it's not the only solution, but it's an important solution because it has two advantages at the same time. So we have gas. Let's say this has been produced by this process by wind energy. It's renewable gas. It can be used in the heat sector, which adds to the decarbonization of the heat sector. Same is valid for industry, of course. Everywhere where you use fossil gas, you can use this renewable gas. It's chemically identical. It's the same CH4. And the best thing is you can use it in mobility to solve the unsolvable long-range mobility problem. As Wolfgang Streicher has said before, even in the Austrian considerations, we have a gap. If we're looking at the fuel sector, we need some solutions for the fuel sector. This is a solution that can be used in the fuel sector. And you can cover, and Orde is now covering all the three: battery electric vehicles for short range, hydrogen fuel cells vehicles for the future if they are fully developed, and if there could be an infrastructure, we don't know yet, and compressed natural gas vehicles for the very near future. I'm going into this in a few moments. So this is the main advantage of this technology. It couples the gas grid and electricity grid and solves a lot of problems. Let's look at other storage technologies and compare them. You still remember this chart where I showed you all the problems that we think that will occur when going 100% renewable. The known technologies I'm depicting here cannot address storage with load times longer than 2 days, and they cannot contribute to solving 100% renewable energy in heat, transport, and long-range mobility sectors. This sentence here is depicted by orange color here. Green means the technology will be, in principle, able to solve the problem. So we can solve problems in the distribution grid by using storage technologies like pumped hydro storage, using batteries, electric vehicles, batteries. We can use hydrogen stored in tanks. We can use redox flow technologies. We can use compressed air adiabatic storage, things like that. These are all technologies that some are developed and will be available in 2020 plus. Some are available today, like battery electric vehicles in some stage of development. But still, if we take all these technologies, there are three things that cannot be addressed, and these are important things. Because you saw, we have a lot of times where we have storage times longer than 2 days, and we have a problem with heat and industry, because heat and industry together is 60%, and mobility is another 20%. Long range is maybe a share of this 20%. But in overall, we need more than 50% of the problems. We can't find a solution with the current technologies. And this power-to-gas thing, as it takes the existing infrastructure, it doesn't add anything to the infrastructure. And it produces a gas that can be immediately injected into the infrastructure without any other complications. It solves, in principle, all the problems. Of course, there's matter of potential and so on, but this is a technology that in principle solves problems that could not be solved before. So you might say this is a German problem. The Germans are crazy, they want to become 100% renewable, and they will also earn money with it because they build all the technologies. I think this is right. They will earn a lot of money by building it, and this is a German thing, of course. But Austria might also profit, I think, by building renewable energy. And also, it's not only Germany who will suffer the problems when going renewable. Everybody in Europe will have to go in some or the other way renewable, because the EU is focusing very hard on this. Wolfgang Streicher showed a chart to that also. I give you another example, just to go out of Germany for one moment. UK and Ireland and Germany have similar problems when building up renewable energy. The problem is that the wind potential is largely situated west of Ireland. And the industry is situated more in the UK. And the same is in Germany. The wind is situated in the north of Germany, whereas this industry is situated in Bavaria and Baden-Württemberg. And so we will need a lot of electricity transport facilities like transmission power lines from here from north to south and here from west to east. So you can see, this is just, of course, a schematic picture, but it shows that there will be similar problems when going to other countries. It will not be the same problems everywhere, but even in UK and Ireland, there will be a similar problem. Now let me show you the status. Where are we? Is this just an idea, or are we building something? I would like to show you that we are building something. Let me show you from idea to reality. You might have noticed that I'm coming from a company that is called Solar Fuel initially, and now I'm working for Audi. How does this come? Solar Fuel has invented together with the Center of Solar Energy and Hydrogen Research in Stuttgart this technology. These are people from this ZSW. They have built a prototype in Stuttgart. The prototype demonstrates two things. First thing is, it's possible to take CO2 from the air, to strip the CO2 nearly completely from the air and use this CO2 in the methanization process. This is also something that had not been demonstrated to that date. But this is something that Wolfgang Streicher said before, we could do this. The problem with this is you lose a lot of energy. The efficiency decreases dramatically when you have to strip the CO2, the 400 ppm, out of the air, of course. So it's better to use 100% CO2 sources as long as they are there. And now I can say, fortunately, we don't have a problem with 100% renewable, 100% CO2 sources. There's a lot of CO2, there's too much CO2 everywhere. So we just have to take the CO2 that is there until it's not there anymore. This is this this is a container. These are two 20-foot containers. And this container is this absorption technology where it takes the air and strip the CO2. This is the methanization container. This is the electrolyzer. And the methanization unit is very small. It's just some tubes which are located here. And when you look at the back of the container, you can see some pressure flasks. These are flasks that store the gas that is produced during the process. And there's also a fuel maker here who produces this, who makes the pressure of 200 bar to fill it into a CNG car. So what has been demonstrated with this pilot plant, it's a 25 kilowatt, a baby plant. It's a very small plant, but it fits into a container. And it can produce the gas that is needed for a tank of a car to tank one car for one day. But it was just a demonstration plant, of course. This was in 2009. Currently, Solar Fuel, which is the company that has developed this together with ZSW, is working on a 250 kilowatt alpha plant, so also some kind of prototype with some other features. And Audi builds the world's first megawatt-size power-to-gas plant now. It will go live in mid-2013. This is the plan. It's a high-risk thing because we are ramping it up from 25 kilowatts, then 250, and then go up to 6 megawatts. This is a crazy thing to do, and Audi was crazy enough to do it. And that's why I'm working for Audi now, because I'm responsible for also building this plant. So Audi wants to show something. Audi wants to show balanced mobility is possible. 100% renewable mobility is possible. And also they want to demonstrate that they see their responsibility not only to make a car that runs on a 100% renewable gas, but also to produce the gas, because it's useless if you produce a car and tell everybody else to produce the fuel. You have to produce the fuel yourself. And Audi is the first in the world, and this is why I was fascinated by this, who was daring to do this. To do that, the VW VW Kraftwerke, a part of the VW concern, they buy wind energy turbines, also to show that they invest also in the wind energy. The wind energy will be fed into the grid, and then on times when there's too much energy in the grid or when the energy is very cheap, the energy will be extracted. The energy will be fed into the electrolyzer, the hydrogen will be produced, and then the E-gas, this is the synthetic methane, will be produced in the methanization unit. And in the end, you can tank a car on the 900 gas stations that are now currently in Germany. And this is the new Audi TCNG. It's a model that will also come out next year in 2013. It's an A3, and it will be have all the comfort of a normal A3, but it will run on 100% renewable methane. Thank you very much.
Thank you very much. That was very convincing. Lots of questions here. My goodness, lots of questions. I will use the privilege as a chairman to ask the first question. How much energy do you lose when you transform electricity to gas?
The efficiency is 60%. We're aiming at 60% for the gamma plant. This is a beta plant, which means it's also following the prototype plant. It will have 54 plus minus 3%. So well, this is the target.
Okay. That's a good target.
Power to gas, yes. Not power to power.
Yeah. Yes, sure. Okay. Michael, will you help me with the microphone? Will you...
Yeah, I was just trying to find out how much time we have, because we are already 9 minutes past 8.
Yeah, and indeed,
I propose only 15 minutes because we have to leave here and we should...
At this point, Michael, I want to pass over the chair to you because I have to go to the airport and produce some CO2. So I really have to go to the airport right now. So will you chair this discussion, please? Thank you all.
Oh, okay, hello. Nein, nimm gleich das. Okay. No, I really think that we do not have the chance to really have a round here. But of course, I ask you to be out there. But there will be only 15 minutes left, so there will be a couple of questions. But of course, please come up here. So now I have the difficulty to who will be allowed to ask the 3 or 4 questions. Okay, you were the first.
Hi, Greg Rock from the US. I want to dig in a little more to this efficiency. I'm assuming you're quoting that that's a free CO2 going in the process. If you look at carbon capture and storage, the bulk of the energy that goes into that process is capturing the CO2. So even if you're not stripping it straight from the atmosphere, there's a lot of energy that goes into the capturing of a pure CO2 stream. So I'm curious how that would affect the efficiency. And you pointed out it's not round-trip efficiency going back to electricity, but this is an interesting concept if you have unlimited renewable energy. But you apply this round-trip, it's not storage. You're looking at being probably around 20% round-trip efficiency, if you're using a natural gas to electric at 40% efficiency and you're running a 50% efficient process, which might even be lower when you have to strip the CO2 from either a very concentrated CO2 stream or an atmospheric one. So kind of curious about, could you lay out some more specific round-trip efficiencies for different scenarios? Because there's a lot of different things going on there.
Yeah, thank you for this question. Let me tell you, let me answer the first question first. Where do we take the CO2 from this beta plant? And we are planning to do this for the next plants too. The CO2 comes from a biogas plant. And the biogas plant will be using an amine scrubber. And the amine scrubber itself uses heat. And the heat comes from the exothermic methanization process. So there's no loss in energy using this amine scrubber in this case. But you're of course right, if we would use a CO2 from, let's say, a coal-fired power plant or something else, then there would be more energy needed to scrub the CO2 from 12% CO2 in the exhaust gas of a coal-fired power plant. But in our case, this 54% plus minus 3 will be the overall efficiency. Even we will increase the overall efficiency of the biogas plant because we will be using the excess heat that is produced in this exothermic process in the biogas plant to heat, for example, the waste materials coming in. It's a hygienization process. But this is very detailed. We can talk after it, if you like, in more detail. For the second question, this is why Audi is going using this as a fuel because because of course you're right. If you're going round trip, if you feeding the gas into a gas-fired power plant, you lose again a lot of energy, and you end up with 35 maybe if you're good. Okay, overall efficiency. But the thing is that efficiency is not all of the game. The main thing is that you have the emissions needs to be very low, and also to consider the emissions, you have to calculate the life cycle analysis of the cradle to grave of the whole process. This is one of the things that should be considered. The other thing that should be considered is how much does it cost. And we are targeting at costs. This will not be reached at this plant, of course, because it's a demonstration plant. But in the near future, we are targeting at biogas prices in Germany, which are between 7 and 9 cents per kilowatt hour. And then you have to compare, you have to see if this gas, if we can produce it for 7 to 9 cents per kilowatt hour in Germany, if this gas finds a market in Germany. And then you have a solution or not. And if you can use this gas for reproducing electricity from the gas, it will be dependent on this price you can produce. In any case, we think that in the near and for sure in the far future, this technology will be economical. And we know already, because we made life cycle analysis with various institutes, that this technology is unbeatable in CO2 emissions if you consider a car. We have CO2 emissions that are as low as a battery electric vehicle, cradle to grave, run by wind. If we feeding in 100% renewable energy, just wind energy in both technologies, then we have the same complete emissions. It's lower than 50 grams per kilometer, cradle to grave. Okay, it's not the usual emissions, it's the cradle to grave consideration. Okay? If you have some more detailed questions about the CO2 and so on, we can talk about it later.
I do come from an organization where the next question always goes to a woman, if there is one. If not...
Can you fill me in? I'm missing something. You're generating hydrogen and you're making synthetic methane. By my reckoning, you've got to expend as much hydrogen to get rid of the oxygen because you're going to produce 2 moles of water. Mm-hmm. So 1 mole of methane, 2 moles of water.
That's right.
So how can your efficiency be more than 50%? Because half your hydrogen that you've spent a lot of energy producing is going straight out the door as water, and there's still a fair amount of energy that you're going to have to input into the methanation section to produce the methane. I don't think your numbers add up. 54% I think is highly optimistic, because you've also got a loss in the generation of the hydrogen.
Okay, I can tell you how we calculate the efficiency, if you like.
Well, it certainly doesn't sort of seem to fit the efficiency as I understand it, which is the thermodynamic efficiency.
That's why I'm telling you how I calculate it. The efficiency is calculated by taking the energy that is coming out and dividing it by the energy that is coming in. And if we do this, we end up with 54%. This is solar fuel, a solar fuel value that is even in the contract with Audi. So solar fuel is quite optimistic to get it. And the value comes by multiplying 2 efficiencies in principle. You have an efficiency of the electrolyzer. The electrolyzer has efficiencies between 50 and 65%. 65 is laboratory, but let's say it's about 60%. And then you multiply it with the efficiency of the methanization reactor, which is 82%, even in the prototype. And then you end up with this 50 to 60%. I mean, we can maybe also, because it's also a detailed question, if you want to do the calculation, we can sit together afterwards and then, or exchange emails or something, then I can show you how I calculate it.
So, I see 2 more hands, so you will be the last ones.
Thank you.
Because the other group in the other session already finished. And
hi, my name is Fabian Gasmier, film producer from Berlin. This is a very quick question. If you have an efficiency of 54% and you want to achieve a price of 9 cents per kilowatt hour, you have to produce the renewable energy for 4.5 cents roughly. How do you want to achieve that?
You mean the price for the electricity needs to be about that?
Yeah, exactly.
That's right. And how is this? This is the main thing that can be done by the technology. Can I have this switch again? Okay, but never mind. But you remember the chart with a red and the blue, okay? With a red deficit and the blue surplus. This technology can switch on within 5 minutes at the moment. This is an electrolyzer problem, so we could even do faster if the electrolyzer would be better. We can switch on within 5 minutes, so we can really switch on when we have very low electricity prices. At the moment, we are one of the possible methods that would work today is to take secondary control power, to offer secondary control power, which means you are a controllable load for some energy provider, for a grid operator, in fact. And the grid operator will switch on the electrolyzer in exactly when he needs it and switch it off when he doesn't need it anymore. And then you get prices that are even lower than 2 cents per kilowatt hour. There are some games doing this, but you are addressing an important question, how to get cheap electricity. But in principle, the technology can harvest exactly the electricity prices that are low. And this is the main thing. If the technology could not do this, it would be useless. It has to do this. And if we make a little step in the future, you will see that renewable energy makes one thing for a price line. The price line, if you order the prices by the hour, you get a price line with the high prices first and the very low prices afterwards, okay? So you have a price line, let's say this is the y-axis, the price line will be a bit like this. And the price line with more and more renewable energy will skip like this. There will be very low prices for 2,000 and more hours, and there will be extremely high prices for 2,000 hours. And we are aiming, of course, at harvesting the very low prices. But all kinds of studies we made show that we will reach these 7 to 9 cents per kilowatt hour for the gas. Okay? Thank you for the question.
Okay, that's Christoph Kiener from ASPO Germany. A question on your intermediate product, hydrogen, which is also a commodity in chemical industry and in industrial gas business today. If we look how hydrogen is made today, it is made from natural gas. So you make hydrogen from electricity and convert it into natural gas, and there are others who convert natural gas to hydrogen. So wouldn't it be more wise to put an electrolyzer to such a plant which converts natural gas into hydrogen and to save the natural gas and to use the hydrogen instead from the electrolyzer?
That would be, this idea has been considered, and there are some people working on it. It's a good idea, but the point is not to produce hydrogen for the sake of hydrogen, but the point is to, on one hand, harvest energy that is not needed in this very hour or in this very minute, and on the other hand, produce something that is renewable, which needs. So, if you make hydrogen from fossil gas, it's not renewable. That's the problem.
Yeah, but you would save much more gas than you produce.
Yeah, okay.
And in the end, there's more. If you substitute, or if you put an electrolyzer to a steam reformer, which makes hydrogen from natural gas, and just inject this hydrogen in the normal product and reduce the load of the steam reformer, then you save more natural gas than if you produce natural gas from the hydrogen you made with electrolysis.
Okay, let me just tell you.
And in the end, there's more natural gas in the storage.
I would like to give you one example out of the studies we are doing with people who exactly want to do this idea. One of the problems is that the industrial process would need the hydrogen at a constant rate, at a certain rate. And we are working on, there would be some intermediate storage because we are producing hydrogen at a non-constant rate. We produce hydrogen when there's excess energy available somewhere. And so you would need to integrate this technology using some intermediate storage tanks and so on into the industrial process. But we can, let's talk afterwards and find some solutions for it because we are working on this problem anyway. Thank you very much.
I also thank you very much. As I'm not a professional moderator, I finish without saying anything.